Good afternoon and welcome to the first of two CIBSE Natural Ventilation Group webinars on acoustics and the natural and hybrid ventilation in buildings. The first one today is on residential buildings, and our second webinar will be on Tuesday the 8th of May at the same time as today, 1 p.m, and you can register online via the CIBSE website. I'll give you a bit of contextual information first about why we decided to run these webinars, and I'll introduce you to our two speakers. My name's Benjamin Jones. I'm an assistant professor at the University of Nottingham, and I'm joined by my colleague Sean Fitzgerald.
Hello, and I'm Sean Fitzgerald from the Royal Institution. I'm the director here, as well as CEO of Breathing Buildings and a visiting professor at the University of Cambridge.
Great. Naturally ventilated buildings use openings located in their facades to simultaneously supply fresh air and extract air. However, these openings also allow the ingress of environmental sounds, which when they are unwanted, unpleasant, loud, or disruptive, are defined as noise. The very size of natural ventilation openings is a problem because it means that noise ingress can be significant. And an unintended consequence may be that occupants seek to control noise by closing those ventilation openings, which has in turn consequences for underventilation, poor air quality, and overheating. There are solutions, and we're going to discuss some of those today. In the context of residential buildings, noise is often given consideration in the planning process if a local planning authority identifies any significant noise sources affecting a proposed residential development. The assessments generally refer to British Standard 8233, which indicates noise levels based on World Health Organization community noise guidelines that in turn attempt to avoid adverse effects of noise on people. However, there is no explicit guidance on how to consider the effect of ventilation provisions. The Professional Practice Guidelines on Planning and Noise, ProPG, was released last year, and this gives good acoustic design within the context of government planning and noise policy. To provide guidance on how to undertake assessments of noise, the Association of Noise Consultants, the ANC, has published for consultation its Acoustic, Ventilation and Overheating Residential Design Guide. And to discuss these issues and these documents, we're delighted to be joined by Jack Harvey-Clark from Apex and Anthony Chilton from Max Fordham. Jack Harvey-Clark is a founder of Apex Acoustics and the current chair of the Association of Noise Consultants. He's also a board member of the Airtightness Testing and Measurement Association. Jack has grown Apex to 15 members and provides consultancy and testing in acoustics and airtightness across the construction industry. Anthony is the head of acoustics at Max Fordham LLP, having been at the company for 14 years. He's also the chair of the ANC Acoustics, Ventilation and Overheating Working Group. He's also published a number of conference papers in the area. I will hand over to them now and they will tell us about these issues. Jack.
Thank you very much, Ben, for the introduction. So I'm Jack Harvey-Clark from Apex Acoustics, and I'm going to introduce the subject today and take turns with Anthony to present you what's in the guide and what the implications of it are. So this is about the design of residential accommodation and how we can consider acoustics within the ventilation and overheating provisions. So I'm going to talk about the introduction, the context of the guide, why we need the guide. Then I'm going to hand over to Anthony to talk about how the guide considers external noise sources. I'm going to talk about mechanical services noise considerations. And then Anthony is going to talk about integrated design solutions and case studies. I'll talk a little bit about the design process at the end. So first of all then, why do we need a guide? Well, you may have had an opportunity to look at TM60, Good Practice in the Design of Homes, which talks about the need for integrated design solutions to achieve or an integrated design process to achieve passive solutions. That's certainly the case. Our experience, if we look at the current state of the industry, what goes on at the minute? So where we carry out facade sound insulation assessments, these are required for planning, as Ben mentioned. So the assessment is considered by usually the Environmental Health Department, who the planners refer to on matters of noise. The ventilation strategy may not even be determined at the planning stage, and it's going to be monitored through the building control process anyway. Because building control and planning are separate functions, they don't need to coordinate with each other. So there may be assumptions about the windows being closed to achieve reasonable internal noise levels in the facade assessment, whereas the ventilation strategy may actually require windows to be open for part of the year to achieve reasonable internal air quality. We know that overheating assessments aren't regularly carried out everywhere at the minute, but here obviously we have the assumptions. What we always suspected was that the overheating assessment may assume that windows will be open when the facade sound insulation assessment will assume that the windows will be closed. So my colleague Nick Conlon presented a paper at the Institute of Acoustics just on Monday of this week, in which we reviewed 160 planning applications in London between 2014 and 2017. So we just looked at the major developments for more than 100 dwellings. And what we found was that 85% of them made this assessment, where the windows were assumed to be open for the overheating assessment and closed for the acoustic assessment. So what we're doing at the minute is, in general, designing dwellings and allowing people the choice of reasonable noise levels or reasonable temperatures, but not both. So I'm sure you'll agree that's a pretty embarrassing state for our industry, really. So we were aware of this a few years ago. There's another issue about noise from domestic mechanical ventilation systems that I'll talk about later on. But first of all, we need to understand the context for noise in the planning process. So we have the National Planning Policy Framework and the Noise Policy Statement for England, which talk about how noise should be treated in the planning process. We're all engineers, so what we like is clear design criteria that we can design to and we know that we can achieve them. But planning refuses to give us clear criteria like that. Rather, noise should be considered in terms of its adverse effects. So what this means is, if I show you a picture of a dose-response relationship for noise. So along the x-axis, we have the sound level, and on the y-axis, we have the prevalence of high annoyance. So each one of those dots within that graph is the result of a study, a separate study on the prevalence of annoyance depending on the sound level. So you can see the extremely wide range of responses in terms of annoyance to different sound levels that you get in practice. What planning says is that we need to mitigate and minimize when the sound level goes above what's called the LOL, or the lowest observable adverse effect level. So whilst noise might have an impact on health and well-being, but it doesn't have any adverse effect, we don't need to worry about the level. So let's say that's there, for example. So below that level, there's no acoustic constraints in the design. Above that level, we need to mitigate and minimize as far as we can, until we get to a higher level where there's a significant observable adverse effect level. So we should avoid any impacts above a significant observable adverse effect level. So although there's wide consensus on where that green dotted line may be for different room types, for daytime and nighttime, bedrooms and living rooms, there's not much consensus on where the SOL might be for different types of living rooms, bedrooms, and at different times. And planning itself refuses to give any numbers because that suggests that in different contexts, different noise levels may be acceptable. So to fill the void in the absence of guidance, as Ben mentioned again, the professional practice guidance on planning and noise was produced last year by a group of people who were members of the Institute of Acoustics, Chartered Institute of Environmental Health, and the Association of Noise Consultants. This describes what good acoustic design is, so how to consider acoustics from an early stage in the design process, in the site layout, orientation of buildings, so that as many residents as possible can enjoy reasonable internal noise levels with open windows. But it says where you rely on closed windows to achieve reasonable internal noise levels, then you should design the accommodation so that it provides good standards of acoustics, ventilation, and thermal comfort. And it says that because our group in the Association of Noise Consultants suggested that would be suitable text. So we've been working since about 2016 to put this guidance together. We're composed of members from across the industry, both independent consultancies and multidisciplinary consultancies. We've also had some input from environmental health practitioners and some mechanical engineers. So I'll hand you over to Anthony now to talk to you about the contents of the guide.
Okay, thank you, Jack. So Jack's obviously just set up why we felt we needed the guidance. So what I'm going to do now is I'm going to start describing what is actually in the guidance. And to start with, we felt one of the most important things for us to do at the outset was to distinguish between the different situations where different noise criteria might apply. And that's what's represented by this table here. So they're basically 4 conditions, and they arise by the combination of 2 different environmental conditions and 2 different sources of noise. So the environmental conditions are the ventilation condition, and that's when you're providing ventilation as described in approved document part F. And then there's the overheating condition, which is when you're applying measures as required to meet your overheating criteria, for example, as described in TM59. So the ventilation condition is the top line in the table, the top row, and the overheating condition is the bottom row. And then you have the different sources of noise. So you have noise from mechanical services, which is the right-hand column. And you also have noise from external sources, so noises outside the building that break into the building, particularly via ventilation openings. And we, at this stage, have limited the scope to transport sources for simplicity. So in terms of how we've approached the guidance, the mechanical services, we've made reference to the CIBSE A guide, and Jack will talk in a bit more detail about that a bit later on. For noise from external sources, for the ventilation condition, we've made reference to this British standard, BS 8233, which is quite a central document for acousticians, and I'll talk about that in a second. And really for those 3 conditions, we're really just clarifying the situation in that we're making reference to existing guidance, whereas for the overheating condition, for noise from external sources, there isn't really any existing guidance, and that basically is the situation of open windows. And so that was the one where this red splodge is basically to indicate that this was the problematic one. This is the one we spent a lot of time talking about. This is the one where we had to develop our own guidance on what we thought was appropriate way to approach this. And basically it's also the one where there's kind of most collaboration required between the different disciplines in the design, because obviously the overheating design affects the noise situation, and we want to, through this guidance, promote a situation where there's some joined up thinking, and we avoid that situation of different parts of different designers making different contradictory assumptions about the window state. So I'm going to start by talking about box 1, so the noise from external sources for your ventilation condition. And so we make reference to this table 4 from BS 8233. So as I say, acousticians are very familiar with this because we use it all the time, but I'm just going to quickly run through it to describe what's in there. So the figures in this table are average values for the day and nighttime period, and there's different values given for different rooms depending on the activity that's likely to be happening in that room. So for acousticians, the standard daytime period is from 7 AM in the morning till 11 PM at night, and then obviously nighttime is the other part of the day, so 11 PM till 7 AM. As I say, the values are average values over the whole period, and they're A-weighted values, which just means that they've been weighted to account for the sensitivity of the ear to different noise frequencies. So in our guidance, we've clarified that the values in this table do apply for the ADF whole dwelling ventilation rate, which is something that's going to happen all of the time, but they don't apply for the ADF purge situation. And the reason for that is that's only going to happen occasionally, because Part F is pretty clear in stating that purge ventilation is for occasional situations like burnt food or spillages, and so we're not really that bothered about the noise during that situation. So the implication of this is that if you're trying to achieve these BS 8233 target levels inside your building, then there's only certain types of approved document Part F template systems that may be appropriate depending on your external noise level, and that's because the different systems provide different levels of sound insulation from outside on account of the fact that they have different they require different openings in the facade. So if we take the case of a bedroom at night where we're trying to achieve 30 dB inside the room, then if you were to use a Part F System 1 or System 2, then you require trickle vents in the facade, and that effectively limits the sound insulation in your facade such that you can only really use that system for external noise levels up to around 53 decibels in the nighttime period. And I just make the point these are approximate values because it depends on the details of the geometry of the room and all the rest of it, but just these are rough figures. If you then move to a Part F System 3, mechanical extract ventilation for trickle vents, you've still got the trickle vents, but now you've got they can be smaller because you have a mechanical driving force, and they can also potentially be attenuated, and that means that you can consider that system for higher external noise levels up to around 63 dB. And then finally, if you were to use System 4 MVHR, then it's fully ducted. There's no openings in the facade, which means that really the facade insulation is limited only by the other elements of the facade construction, and particularly the glazing. Okay, so that's covered box 1. So now I'm going to talk about the noise from external sources for the overheating condition, so box 2. So as I say, this was the tricky one because we didn't have any existing guidance that we could make reference to. So what we needed to do was to think about the noise effects which are relevant for residential. So for daytime, we looked at interference with activities, and that particularly really comes down to speech. And at nighttime, we looked at sleep disturbance. And so having identified these effects, we then interrogated a whole load of documents from across Europe to look at guidance which might be relevant to these effects. And based on what we could find, we generated this table, which sets out risk categories which are determined by the internal noise levels in the daytime and nighttime period. So it's set out in quite a similar way to the table in Table 4 from BS 8233. So just to run through these risk categories. So to start with, we have the negligible risk category at the top, and that is equivalent to saying that you achieve the values in Table 4 of BS 8233, i.e. that the noise level in your overheating condition is no different from the noise level in your ventilation condition, so that's clearly not a problem. The low risk category is equivalent to saying that you don't exceed the 8233 values by more than 5 dB, and the reason for that is there's a note in 8233 which says that that corresponds to reasonable conditions, so we felt that's a low risk. The high risk category is defined by the point at which the noise starts to significantly have the effects described. So in the daytime, that's effect of speech communication, and we suggest that above 50 dB inside, speech communication is significantly affected. At night, above 43 dB, then a sizable proportion of the population is highly annoyed and sleep disturbed, and we've derived this figure from some guidance by the WHO, night noise guidance, which actually gives the analysis in terms of external noise level of 55 dB, and we've converted that to 43 internally by assuming that a simple open window for overheating control will give you a level difference between inside and outside of roughly 12 dB. So that leaves you then with this medium category, which is effectively just defined by being sandwiched between the low and high risk categories. And the reason I've put a question mark against that is the implication of this table really is that the low risk category isn't a problem. The high risk category is something that probably should be avoided for all but exceptional circumstances. But what about the medium risk category? What do you do with that? How do you assess that category? And the key thing there is that the adverse effects that comes from noise, which is what, as Jack said, is what is relevant for planning. The adverse effect depends not just on the noise level, so not just where you are in that table in terms of the level, but also on how often you're exposed to that noise level. So basically, what the frequency and duration for which you need to open your window in order to keep yourself comfortable. So the implication there is that as acousticians, we need or we potentially need information from a thermal model to understand how open a window would be and how often it will be open. So there's clearly got to be good communication amongst the design team and a decent understanding from acousticians about the issues so that we can engage with that. There's also the implication there that adverse effect from noise can be mitigated not only by reducing the level of noise, but it could also be mitigated by reducing thermal gains, because that then would have the result of reducing the amount of time for which you only need to open your window and therefore reduces the effect. So all in all, this comes back to the idea of having a collaborative design process. And really the document is trying to promote a situation where acousticians come to the design not just with constraints, presenting constraints on the process, as in saying, look, you can't open the windows, which I think is kind of currently a bit how it's perceived, but instead trying to get a situation where acousticians are aware of the interrelationship between overheating, ventilation and noise, and can, instead of just providing a constraint, can come forward in a more positive way with some design solutions and a more joined up process. So having given the guidance about the noise levels, this is the procedure of assessment that the guidance suggests. This is a flow diagram from the document, but the key point really is there's two levels of the assessment, level 1 and level 2. The idea being that level 1 is a simple assessment that should hopefully be suitable for a lot of sites, and the idea being that we're trying to avoid introducing complexity in the process where it's not really required. And then the level 2 assessment is a more detailed assessment. So level 1 is based on external noise levels. So the idea being that the acoustician can simply go to site, measure the noise level and directly do the assessment from that. In order to make this a simple assessment, we've had to make simplifying assumptions. And the key one is that we've assumed that the overheating control method is by use of a simple opening window that gives you a level difference between inside and outside of roughly 12 dB, i.e. your internal noise level would be 12 dB less than the noise level outside the building when you've got the window open. So what that allows you to do then is effectively make the assessment by simply adding 12 dB to the levels that were in the table, the risk category table presented earlier. So for example, you will be in a high risk category if your daytime noise level is over 62 dB externally, or if your nighttime noise level is over 55 dB. And what we're saying that is if this level 1 assessment indicates that you are in a high risk category, then we're recommending that you really then need to do a level 2 assessment, because that's an indication that opening windows aren't a good strategy and you need to do something else. So the level 2 assessment is based on internal noise levels. So this time, instead of just making a simple assumption of opening windows, you look at the actual design of your facade and the sound reduction that facade design will achieve. And then you evaluate the internal noise levels from the external noise levels and the sound reduction of your facade. And then you make an assessment of adverse effects with reference to this risk category table based on the internal noise levels. So that's obviously a more involved procedure because there's more calculation, but the advantage is that it allows you to consider designs for controlling overheating that provide a greater degree of sound insulation than you would get from a basic open window. So for example, attenuated vents, and that's something that I'll come back to a little bit later in the presentation. And so at this point, now I'm going to hand back over to Jack, who will discuss noise from mechanical services.
Thank you, Anthony. So I'm going to describe or talk about how we approach the issue of noise from mechanical services for both ventilation and overheating. So thinking about ventilation, first of all, and to distinguish between the whole dwelling ventilation rate and the extract ventilation condition. So there's a little bit of guidance, a note in approved document F, that continuously running systems shouldn't exceed 30 dBA in bedrooms and living rooms at the minimum low rate. So we refer to that. For the extract ventilation, CIBSE Guide A doesn't appear to distinguish between the different parts of the ventilation condition, but it fortunately refers to the same level of 30 dBA in bedrooms and allows a slightly higher level in living rooms. So we also refer to an older publication, Sound Control for Homes, because it has criteria for some other room types. There is a question though about whether or not 30 dBA is suitable for bedrooms. There was a big European collaboration of acousticians within the cost action TU 0901 that's resulted in the ISO 19488, which is just about to be published earlier this year, as they are. It's an acoustic classification scheme for dwellings, and that contains this table. This is for sound levels in buildings due to service equipment, so it doesn't again distinguish between ventilation or cooling systems. But the highest class is for sound levels to be less than 20 dBA. So you can see from this that 30 dBA would be in class D, and this suggests you should expect 20% occupant dissatisfaction in that class, or 35 dBA would be in class E, where you would expect 35% dissatisfaction. But if we dig a little deeper from the experts and look at what actual evidence there is for people's tolerance of sound levels in their own homes from domestic mechanical ventilation systems, then the best information we have is from, or the only real information we have, you could say, is from this study in Finland in 2007, which was quite extensive, 102 homes, and they were investigating the then Finnish building regulations for half an air change an hour and a sound level limit of 28 dBA. They found this relationship between sound levels in the bedroom and the occupants who found that too noisy. So the bedroom's the most sensitive place because while you're going to sleep, the background noise is quietest and you're being quiet as well. So you're the most sensitive times. This is a cumulative distribution graph. So the first column shows that 10% of people found a sound level of 22 dBA to be too noisy. Because it's cumulative distribution, if we move across the columns to the right, by the time we get up to 30 dBA and add up all those columns, there's more than 40% of people finding that to be too noisy. So this study found that what happened in practice was that people turned their systems down or turned them off entirely until they could tolerate the noise. So they operated their ventilation systems based on their noise tolerance, not on the ventilation they needed to achieve reasonable internal air quality. This finding has been found again by other studies across Europe, but particularly those that have adopted mechanical ventilation in the same way that we have in the UK, which you might describe as rather haphazard and uncoordinated. They've subsequently introduced a mandatory noise limit in the Netherlands to control noise because it was such a big problem there. A more recent study in Canada described that it was the noise in the bathrooms that people objected to, were turning their fans off and not turning their noise up, not turning them on again. And this time it wasn't the level of the noise, but just the quality of the noise that caused the problem. So what do we know about what's happening in the UK then. The Zero Carbon Hub started investigating this because they realised there was a problem there, and they found the same type of thing, although on a rather smaller study. People are turning their systems off because they're too noisy. And our experience of this as well is that people often don't report this. They turn them off and then report they have no problems with the noise from them. But obviously, if they live in an airtight house, they will suffer the adverse effects of poor indoor air quality. So we think that potentially to avoid these problems, and you can read all about this in the paper, which you can get off our website as well, is that 30 dBA is likely to be widely unacceptable, and an optimal limit to avoid adverse effects is likely to be around 24 dBA, we think, and higher levels may be acceptable if the quality is okay. So we're currently involved in a bid to the EPSRC to try and get to the bottom of this. Now, this is not in the guide at the minute, but we'd be very interested if any of you have any experience of people complaining about sound levels from ventilation systems and whether you've had any measurements of the sound from them. So summarising the mechanical services noise issues then, so we're referring to approved document F for the whole dwelling ventilation, the CIBSE Guide A for the extract ventilation condition, and as for external sound and purge ventilation, whilst providing purge ventilation for air quality purposes, as opposed to controlling overheating, there's no acoustic criteria associated with that. And for overheating, simply referring back to the CIBSE Guide again, but with particular reference to section 1.10.10. And that says that a range of plus or minus 5 dB may be acceptable depending on the particular situation. So we can think here that, you go into a hotel room, you turn on the comfort cooling system, it's a bit noisy, but you don't mind because when you want it to be quiet, you can turn it off again when you've got the cooling you need. So there may be times when a higher level may be acceptable for overheating where it's under the occupant's control. So providing advice for acousticians on services noise levels and overheating control then is something which we do in the guide, because many acousticians aren't aware of the details of ventilation and provisions to mitigate overheating. So passive ventilative cooling obviously relies on openings in the facade, as Anthony described. So it's all about the external noise. And there aren't any mechanical systems noise issues unless ceiling fans are used. Mechanical ventilative cooling, if it is suitable or appropriate, obviously it doesn't have external noise level limits, but there are likely to be much higher flow rates than required for whole dwelling ventilation rates. So there's noise from the fans and regenerated noise at grills. There is a question about whether using an MVHR system in a boost mode is suitable. So we understand there are issues around that. Using a mechanical cooling system doesn't have any external noise issues in terms of the internal environment, but obviously the indoor units have a noise issue, and it's worth remembering that the outdoor units are also going to generate noise. We are aware of some manufacturers integrating a small amount of cooling within their MVHR systems, so transferring heat from the supply to the exhaust duct so that no additional equipment is required, and maybe this will be a way they go in the future. So I will hand back over to Anthony now to talk about design solutions.
Okay, so I'm now going to talk a little bit about some design solutions, particularly passive options for the control of overheating, and then also follow that up with a couple of case studies using those kind of passive approaches. So this chart shows a number of options for passive ventilative cooling, and by passive ventilative cooling, what I mean is providing external ambient temperature air at a higher flow rate in order to mitigate overheating, but without the use of any fans or mechanical systems. So what the plot shows is on the x-axis, it shows the outside to inside level difference in decibels. And so that's the difference between the noise level outside your building and the noise level inside your room. And then along the y-axis, you have 4 different types of solution. So the reference one is obviously the standard window, and you can see that a standard window will provide you a level difference of approximately 12 dB, give or take, and that was the value that we've used in the guidance earlier. And you can see that the amount of sound insulation can be improved by using one of these other solutions, and I'm going to run through those now. So for balconies, the simplest type of balcony for providing some enhanced sound insulation is to have a balcony that has a solid balustrade and an acoustically absorbent underside to the soffit of the balcony above, so that you don't get a reflection of sound off that balcony. And depending on the geometry of the balcony and on the geometry of where the noise source is, you can get 3 or 4 dB improvement from this kind of balcony. That can obviously be enhanced further by adapting the design of the balcony so that the balcony is partially enclosed and you get a staggered airflow path. And obviously that's kind of moving towards a semi-enclosed balcony, a bit more like a winter garden type of situation. And you can find some more information about this in the paper that's detailed at the bottom of the screen there. For windows, there's ways of designing windows so that they provide better sound insulation than a simple window. One option is things along the lines of this study that was done in Denmark, where a window, basically a secondary glazed window with offset openings was used, and then there's an acoustically absorbent lining to the reveal of the cavity between the 2 windows. And again, you can find more information about that in the study that's linked below. And then finally, there's the option of using sound attenuating vents. And so this could cover quite a range of different strategies, but it's basically anything where the air is brought in via an acoustically lined element. So that could be an acoustically lined plenum, through acoustic splitters, or through an acoustic louver. And there's a link there to a study which gives some examples of a few different types. The one shown in these pictures here is actually a school, but the principles are the same. So now I'm just going to show a couple of case studies, and these are both residential projects, but they use the attenuated vent type of solution. So the first one is Northwest Cambridge, Lot 5. And this is accommodation for graduate students in Cambridge. It was designed by RH Partnership Architects, and the M&E and acoustic design was done by ACOM. And what this has is, alongside the windows, there's an acoustically attenuated ventilator. The design also includes an external shade, which obviously limits your solar gains and therefore will impact the noise effect, because it will reduce the amount of time that your ventilator needs to be open in order to meet your overheating targets. And this image shows the ventilator from the internal view. The second case study has quite a similar approach. It's St John's Hill in Clapham, which is a residential development for Peabody. And the architect was Hawkins Brown, and Max Fordham did the M&E and acoustic design. Again, quite a similar strategy. You can see that there are acoustic louvers alongside the windows. You can see in the external image and the internal image, and then also in this schematic diagram here. And so these acoustic louvers were approximately 1 meter squared in face area, and about 40% free area, so provided a ventilation area of about 0.4 meters squared. And actually, just for this project, if you're interested, in the link that's on the final page of the presentation, you can go to our website and listen to audio recordings which are done in the completed building to compare the situation with the window open or the vent open. So just to explain the strategy, they're both quite similar, actually, the design. So I've combined them into one slide here. So the external noise levels at the sites was approximately 60 to 65 dB at night outside the building. When the windows and the acoustic vents were closed and you just had the trickle vents open to provide your Part F ventilation, then the sound reduction of the facade was about 30 to 35 dB, which allowed us to meet 30 dB inside in bedrooms at night. And that is consistent with the recommended value in Table 4 of BS 8233, which was discussed earlier. But when the window is open, then you only get a sound reduction of approximately 12 dB, which means that the internal level is going to be at least 48 dB and probably quite a bit more than that. And in the context of the risk categories in the table that was presented earlier, that puts you well into the high risk category. So it's clearly a problem. And that's why the acoustic ventilator solution was considered. When you have got the window closed but your acoustic vent open, then you can get a level difference of 24 dB, which was at Northwest Cambridge, or 27 dB, which is what we measured at Clapham. And that means that the internal noise levels can be kept to approximately 38 dB internally, whilst providing you mitigation of overheating. And again, in the context of the AVO risk category table, you can see that puts you in roughly in the middle of the medium risk category. And both of these projects were actually designed before the guidance was produced. So, you know, this is kind of reverse engineering things a bit, but it just provides some context of how those designs worked. Okay, now at this point, Jack is going to talk about design process.
Thank you, Anthony. So I'm going to talk a little bit about the design process and integrated design, first of all. So we have information about what constitutes good acoustic design in the ProPG, and that's how to consider acoustics from an early stage in the process, so that you minimize the number of places where occupants need to rely on closed windows to achieve reasonable internal noise levels. So but we know that in practice, it's not always feasible to design your site all around the acoustics or any of the other single discipline aspects, because developers usually want to get as many units as they can on a site. TM60, as I mentioned before, also talks about the need for integrated design in dwellings. And I think this is summarised quite nicely in the London Plan Policy 5.9. So we're trying to get a balance between good internal environmental quality for the occupants, but without excessive energy use. And it's also important to consider, I suppose, that those aspects aren't considered on the same balance, because energy is assessed in a different context from internal environmental quality, which is considered in planning. But the London Plan Policy 5.9 and the cooling hierarchy talks about minimising internal heat generation, reducing heat entering a building, and using exposed thermal mass and high ceilings. So the context and aspect, if you like, of the design before it starts talking about services, the passive ventilation, mechanical ventilation, and last on the list, active cooling systems. So we know that we understand when you do your overheating assessment, you have all these inputs into the model that have no acoustic impact, but that you have the designer, if you like, has control, or the design team has control over. And it's not until you get down to the services that where you start to have an acoustic impact. And then, so you could, of course, consider which room types you put on which side of the development to expose them to different levels of noise at different times if you wanted to. So how much can we push back with you as mechanical engineers into the design team to take a holistic approach to the design, so that we don't just rely on services to control it, the internal environment. So looking at the activities that the acoustic designer will undertake with you, we can consider three columns, if you like, of noise and ventilation, and noise overheating. And looking at the rows, it's about, and the process, it's about gathering information, assessing and advising. The gathering information is about determining what the noise environment is likely to be over the site, and if there are any proposals, what they are. So from that, you might get, if there are proposals, you'll you could get a drawing with marked up facades showing where different ventilation strategies may be feasible, or what types of provisions for mitigating overheating might be feasible from an acoustic point of view, along with the noise levels or the risk of the noise. So to conclude, this is something, to produce this guide, and as Anthony mentioned, particularly integrating the aspect of environmental sound with internal conditions. We're not aware of anyone else ever having tried to do this before anywhere in the world, so it is new ground. To make this work, we think you're going to need to embrace your acoustician, and acousticians will need to embrace the mechanical engineers and the rest of the design team. It's certainly true that we're going to need early engagement if we're going to enable integrated passive solutions. And we think failure to engage early is likely to result in mechanical cooling being used, which obviously we want to avoid from an energy performance point of view. We would warn you to expect variable performance requirements from different local authorities, or even on different sites within the same authority, as they take a different view to the importance of internal environmental conditions compared to the need to get residential applications approved. So we will need to develop context-specific approach and solutions. Thank you very much for listening. You can download the guide from this link, and please do have a read. Any feedback will be very gratefully received, and it will make it all better. You can contact Anthony or myself there, and you can find more information on our website or Max Fordham's website, like that. I think I might have. Can you still see my screen, or have I lost it?
I've left the screen on just for a moment so that people can. Well, I'll bring it back to me. Thank you very much, speakers, Jack and Anthony. You've given us an awful lot of information and a lot to think about. We now have just over 10 minutes for a few questions. If you have any, please use the questions setting, which you might be able to see on your GoToWebinar dashboard. And if you pose those, Sean and I will try to talk through those. We may get through two or three of those in the next 10 minutes. I'm going to kick off with one from Dermot Keeney, who notes that the sound pressure levels are measured over 16-hour periods for the daytime, which is quite a long time. He's interested in short period low frequency type noises, for example, in a quiet area, an aircraft flying over and causing a disturbance which could be averaged out over the course of 16 hours. Are there any peak noise thresholds?
Indeed, that's a very good question. So thank you for that. Something we haven't mentioned today is how we treat the noise from single events, which are averaged in acoustic terms over 1/8 of a second. So the maximum sound level over 1/8 of a second, which have a significant impact at night because they interfere with sleep, whereas the impact in the daytime is probably less significant from that, although it might be annoying. So aircraft noise is treated in a particular way because obviously there's big political implications of it and cost implications. But in terms of the noise from events, we haven't got any details in the guide at the minute about how to consider what might be a significant observable adverse effect level for events. So that will be the combination of the noise level and the frequency of events that occur that might interfere with sleep. But there is some consensus forming around that within the acoustics community, so we'll try and get that in the guide.
Thank you very much. Sean, do you have a question? Yeah, so we have a question from Dr. Owen Connick, and the question is there any evidence regarding about the noise susceptibility for people who live in places which are naturally ventilated versus those that have, for example, mechanical ventilation heat recovery units as the principal means of providing background ventilation or assistance with overheating? Is there any evidence that noise tolerances differ depending on what kind of environment people are in?
So a central part of our assumption in the way we've developed our guidance for environmental sound is that where people have control over the environment with an opening window, that they will accept a higher noise level to get the other parts of the environmental conditions that they're seeking. So this is the same, if you like, as the adaptive thermal comfort model, where control means you're more tolerant of the conditions. So we're assuming that that's true for acoustics as well. We don't have any evidence for that.
Okay. There is another question, which is about adaptation. So in terms of just noise tolerance levels as people live in different environments, this is a question from Mark Willis. Regarding, is a person's tolerance higher if they live in a city than in a rural environment? And that will be because of actually just adaptation.
Sure. So there's certainly an effect of habituation, if you like, in that you get used to your noise environment. So people become more tolerant of the noise environment or rely on the noise environment for their comfort. But what we shouldn't lose sight of is that noise can still have physiological effects that impact on health, even when people have become habituated to the noise. So this is, if you like, protecting people from themselves at this point.
So for example, sorry, it's Anthony. For example, at night time, you have the effect of noise can be such that it doesn't actually wake you up, but it changes the your sleep process and takes you out of deep sleep, which can have long-term health consequences without you actually realizing it, and possibly not even reporting it in the morning as an annoyance. But it still has a health effect, particularly you know, cumulatively over many years.
So I just want to take this a little bit further, if I may. I mean, noise is a subjective concept, right? It's where an individual places value on a sound. So I guess the first point is, when we ask people whether they like a noise or not, do they understand what a noise actually is? And then, if you were to open a window, you could let in birdsong, which may be desirable, but it would no doubt increase the sound pressure level inside. How might we account for that?
So character of noise is incredibly important in acoustics, as you say. So birdsong at the same sound pressure level as an annoying type of noise will have a much lower effect. And so that is taken into account in some of the studies in terms of the thresholds for mechanical services noise will be different for those from environmental noise, as will be there'll be different thresholds for road traffic and trains and aircraft. So the character of the noise, it does matter, and I think it's something that's actually really very important for mechanical services, because if you have a very broadband sound that doesn't have any particular characteristics to it, almost like white noise, it's going to be much more tolerable than a noise which has got tonality to it or intermittency that's that you can really focus in on, or something that you attach significance to. So if you can hear I don't know, your neighbor playing some music, that's clearly has a bigger response than a noise without any character to it, and that is something that's quite tricky for us to take account of. There are some ways in acoustics to do that, but I think it's a fair point, and it's something that is worth being aware of.
So can I follow that up with a specific question from Coralie van Reenen, who said, in the instance where you, for example, got music, and in particular lots of bass, so you talk about A-weighting, what Coralie's asking is that, have you got any suggestions for practical solutions that you might consider in the design of a residential dwelling as to how you might overcome that, or at least provide sufficient attenuation thereof?
So if the noise from outside, external noise, is dominated by low frequency, then that is significant, because the performance of some of the passive solutions that we showed are very frequency dependent, because for example, attenuated ventilators work much better at high frequency, because they're basically they work on friction, which is better at high frequency. And so they won't be as effective at cutting out low frequency noise. And I think it's just one of those things you just have to look at a case-by-case basis. And it might be that in some situations you really haven't got much option other than to use a sealed type of solution with mechanical ventilation. I mean, there's often talked about using active noise control for passive ventilation solutions, but they're not that well developed commercially, those kind of solutions. And it's probably a bit of a specialist type of design.
Okay, so this is a question from actually me, and this is obviously today's webinar has been on acoustics and ventilation in residential dwellings. I'm thinking ahead also to next week, but actually, what happens in building types where, frankly, you've got people who are wanting to stay overnight, for example, in a hotel, and what regulations should they be applying when, frankly, those people are thinking of it, they're wanting to move into a space which, to all intents and purposes, is going to be their home for the night, but it isn't a home, it's actually it's a business. So what's your advice in terms of just when you've got this kind of building type that might straddle both kinds of sort of sets of sort of thinking, but for how do you cope with that as a designer?
If you like, that issue is already addressed by those hotels who are very careful about their brand standards for acoustic performance and know what they need from their ventilation systems and their control of overheating. So people tolerate in those sorts of spaces higher noise levels. That's kind of culturally acceptable. It seems that you expect it to be noisy when you turn on the overheating control, the comfort cooling. But those hotels are very careful to make sure that the ventilation systems, whether they're natural or mechanical, are limited to very low noise levels because they know their customers' tolerance of noise. So that's driven obviously commercially much more strongly than at the minute the regulations drive residential accommodation and that people occupy themselves, so their own homes. Okay.
So Ben, have you got any questions?
Yeah, so there's one here from Nikhilesh Patil who talks about your study, Jack, that was you and your colleague presented last week. About 85% of planning applications assessed did not look at acoustics and ventilation together. Can you elaborate a bit more on the other 15%, please?
Oh, there are some enlightened designers out there.
So they really were. They were considering both. There weren't any sort of left field options.
Apart from the people who are either on this call or work for either Max Fordham or now for Apex Acoustics, we're only aware of one other company who've tried to design an attenuated passive ventilative cooling solution. So those other ones come into the other 15% of or they rely on mechanical systems. So for the windows closed for the mitigation of overheating.
Okay. So as Sean asked one of his own questions, I'm going to ask one of my own questions, and probably the last one for today. So I've always been fascinated by figure 1.6 in CIBSE Guide A. It's on page 1-16 for anyone who's got it to hand. And what it shows is that as temperature increases above around 18 degrees in a bedroom, the quality of sleep starts to drop off, and perhaps highlights just how important sleep is to us. And I was doing a bit of cursory research before the webinar and see that the NHS says that 1 in 3 people in the UK suffer from poor sleep. Long-term effects include obesity, heart disease, diabetes, shortened life expectancy. So it's not great. Do you think we should be focusing more attention on the bedroom? Are there any studies of sound pressure levels in the bedroom? And do you think we're actually achieving 30 dBA in practice?
Okay, so that's an interesting question. There are lots of studies on how noise affects sleep. So sleep studies that are either carried out in sleep laboratories or field studies in people's homes, and you can imagine you get different results in each, where they play people's sounds while they're asleep and measure their response, their physiological response to the sounds, the type of sounds and the level of sound. And then there's the kind of public health approach, if you like, of looking at noise levels in an environment and looking at instances of health effects, heart disease and things like that. But this particular question about people's tolerance to noise in the mechanical ventilation systems isn't when they're asleep, but it's when they're awake but trying to get to sleep. So it's all about annoyance. And this, people who are annoyed at much lower levels of sound than will adversely affect their sleep. And they will then take action against their ventilation systems.
Okay, thank you very much, Jack and Anthony, for your contributions today. I've learned an awful lot, and thank you very much for your time and for your presentations. Thanks too to my co-host, Sean Fitzgerald. We hope very much to see you next week, Tuesday the 8th of May, 1 p.m. Please sign up in the same way. The web address is at the bottom under our events page. We very much hope too that slides will be available in the near future on the Natural Ventilation Group website. So thanks again for joining us. We hope you'll join us again next time.
Thanks ever so much, everybody.